Imagine stepping onto a scale on Monday, only to find that by Friday, your weight has mysteriously plummeted by 99%. The scale still reads the same, yet the numbers make no sense. This is the perplexing paradox of science, one that has just unfolded with the enigmatic interstellar visitor, Atlas, in December 2025. A groundbreaking study upended everything we thought we knew, revealing that our entire understanding of this object was completely wrong and no one saw it coming. What was believed to be a massive 5-kilometer wide giant turned out to be a mere 1-kilometer pebble. The mass, originally estimated at a colossal 33 trillion kilograms, now measures a mere 260 billion. Yet, astonishingly, both figures might be right. If that's true, then either our grasp of cosmic objects is deeply flawed, or 3I, Atlas is defying the very laws of nature. And that's a mystery we're not used to facing. What we thought was a massive 5-kilometer wide behemoth was, in reality, a mere 1-kilometer pebble, the object's mass, originally estimated to be 33 trillion kilograms, now measured at just 260 billion. But here's where it gets truly unsettling. Both numbers, despite being so wildly different, might be accurate. If they are, then either our understanding of how objects traverse the cosmos is catastrophically incomplete, or 3I, Atlas is behaving in ways that defy the laws of nature, and that's not something we're accustomed to dealing with. Stay with me here, because this mystery is only going to deepen as we dig deeper into the layers. If you're as captivated by this paradox as I am, make sure to subscribe so you don't miss a thing as New Delta continues to reveal more about this unsettling enigma. Leave a comment letting me know where you're tuning in from, what time zone you're in, and whether you think we've truly unraveled the mystery of 3I, Atlas, or if it's still hiding something far more elusive than we could ever imagine. Part 1. This object just lost 99% of its mass. Prepare yourself for a startling revelation. December 11th. Liaotenling Arshawu saw the publication of a paper that sent shockwaves through the scientific community. It did something that few astronomy studies ever do. It didn't simply adjust our understanding of interstellar object 3I Atlas. It obliterated everything we thought we knew. The calculations, the models, the predictions, each one was radically off. And by a factor of 120, let me put that into perspective for you. For months, astronomers believed that 3I Atlas, a visitor from the far reaches of interstellar space, was a massive object, the size of a small moon. They tracked it, measured it, and estimated its mass at a staggering 33 trillion kilograms, a number that conveyed an imposing, unyielding giant, a floating mountain in space, unaffected by the sun's rays and other cosmic forces. But when the December study landed, it hit us with the truth. The object was not a 5-kilometer giant at all. It was, in fact, a fragile pebble no bigger than 1 kilometer across. A cosmic illusion. Now, you might wonder, how is that possible? How could we have been so far off? The numbers didn't just change slightly. We're talking about a complete overhaul of our understanding. From a colossal object to something so light, it could be pushed around by forces we typically ignore. A true cosmic conundrum. Imagine for a second, you're standing on a scale, expecting the same weight you've carried for years, only to find it 120 times lighter. How would you explain that? How would you reconcile such a discrepancy? But here's where it gets even more perplexing. You see, mass isn't something we can measure directly when it comes to objects millions of kilometers away. There's no cosmic bathroom scale to weigh interstellar visitors. Instead, astronomers rely on indirect methods, light measurements, assumptions about size, density, and volume to infer the object's mass. Adjust any one of these assumptions, and the final result can shift dramatically. But the discrepancy we're witnessing here is no simple tweak to our assumptions. This is two completely different realities existing in the same space. And it's not something we can just explain away. The old estimate told us we were dealing with a stable, slow-moving giant. capable of shrugging off the effects of solar radiation and outgassing. The new data paints a picture of a much smaller, more fragile object that reacts easily to even the smallest of forces. The scale of this discrepancy is so vast that it's impossible to reconcile them within any reasonable margin of error. So, what's going on here? Is one of these numbers wrong? Or are both correct in some twisted, unimaginable way? We're looking at a fundamental breakdown in our understanding of how these objects behave. Astronomers are left staring at the numbers, unsure of which one reflects the truth. And the community's reaction, it's not disbelief or outrage, it's confusion. Quiet, unsettling disbelief that builds slowly. As if something fundamental has been overlooked. Something has gone wrong, but no one can quite put their finger on it. This isn't just a case of scientific revision. A revision is when we discover a miscalculation or better equipment sheds new light on the data. This is something deeper. This is a scenario where two highly skilled teams have looked at the same object and arrived at completely opposing conclusions. One says the object is a giant, the other says it's a fragile pebble. The fact that both of these data sets exist is unnerving. One of them has to be wrong. But which one? These numbers simply don't match up within any reasonable margin of error. They depict two completely different realities. One is a colossal, ponderous giant, a cosmic leviathan that glides silently through space, shrugging off the effects of solar radiation and outgassing as though it were impervious, much like a battleship cutting through ocean waves without a care. The other, however, is a delicate, fragile object, a mere speck in the vastness of the cosmos, one that is easily pushed off course by even the faintest cosmic forces we hardly notice, a disparity so vast that it creates a chasm between these two physical states, leaving us to wonder which one is true. And yet, the term revision simply doesn't do justice to the scale of this revelation. A revision occurs when you realize you've miscalculated something trivial, or when new instruments provide a clearer picture. But this isn't that. This is something entirely different. This is about two teams of highly competent scientists using state-of-the-art equipment and methods, looking at the same object and reaching conclusions that are, quite literally, worlds apart. Their conclusions can't both be true. Not in any world we understand. One of these realities is wrong, or, and this is where it takes a darker turn, maybe both datasets are somehow correct, meaning that our understanding of the basic laws that govern objects in space is deeply flawed, perhaps irreparably so. Inside the astronomy community, the reaction has been telling, not outrage, not even skepticism, but confusion. A quiet, unnerving disbelief that washes over you when the numbers no longer make sense. It's the kind of discomfort that creeps into your thoughts when you realize that something fundamental about the universe is slipping through our grasp. Yet, no one can seem to pinpoint exactly where the flaw lies. Researchers have begun referring to this as a physics paradox, which is academic speak for saying, we have absolutely no idea what's going on here. Because if the December data is accurate, then everything we thought we knew about 3i Atlas up to that point must be wrong. But if the earlier data is correct, then the December measurements are indicating something impossible. So, which version of reality do we cling to? This is where things start to spiral. If both datasets are valid, and if both teams have measured what they believe they measured, then it's clear that one of our foundational assumptions about how mass behaves through motion is fundamentally flawed. And that's not just a minor issue, it's the kind of problem that ripples outward into everything we thought we knew about orbital mechanics, about how we track near-Earth objects, and how we navigate spacecraft through the endless expanse of our solar system. The object itself didn't change between these two observations. What changed were the equations. And now, we're left staring into a gap that shouldn't even exist, trying to reconcile two drastically different interpretations of the same object. Should we trust the 5-kilometer giant that dominated the headlines for months, or the fragile, lightweight imposter that appeared in December, carrying only 1% of the expected mass and somehow fooling every telescope that observed it? Here's the unsettling part that continues to haunt me. Physics doesn't do paradoxes, not real ones. Anyway, paradoxes occur when human understanding fails to grasp the true nature of reality. They're the product of our models breaking down, unable to capture some crucial aspect of how the universe works. And when we faced genuine paradoxes in science before, whether it was Mercury's orbit, the ultraviolet catastrophe, or quantum entanglement, the resolution always required a complete overhaul of something we thought was settled, something that was foundational. So, which of our assumptions will we have to rethink this time? Is it our understanding of comet composition, our models of how mass is distributed in interstellar objects, or is it something far more profound? Something that challenges the very way we infer properties from distant, unreachable objects. The December paper didn't just throw a number into question, it challenged the entire framework we've been using to understand objects that we can't touch, sample, or measure directly, and that's where things get unsettlingly complicated. If the framework we've been relying on for decades is cracked, if there's a fundamental flaw in the way we think these objects behave, then 3i Atlas might just be the first in a long line of paradoxes we haven't even begun to notice yet. Before we spiral into a void of uncertainty, wondering whether physics as we know it is still valid, we need to look at the December paper more closely. Because the mass discrepancy is merely a symptom, the real mystery is hiding in something far stranger: non-gravitational acceleration. Part 2, the December paper. You would think the paper that triggered this intellectual avalanche would have generated more excitement, but instead, the response has been more subdued. The paper, written by Forbes and Butler, was published on December 20th, 2025, though it first appeared slightly earlier. If you're familiar with the way academic astronomy works, you know that papers like this usually don't cause immediate upheaval. They get published, discussed at conferences, peer-reviewed, and gradually integrated into the scientific discourse. This paper should have followed that typical path, but it didn't. It didn't, because hidden within the data was a measurement that refuses to align with anything we thought we understood about 3i Atlas. That measurement is called non-gravitational acceleration, or NGA for short. You might have heard the term before, but it sounds far more exotic than it really is. Let me break it down for you. When tracking an object moving through the solar system, we expect it to follow a predictable path based on gravity from the sun, from the planets, from everything around it. If you know the masses and positions of the objects involved, you can calculate with precision where that object should be at any given moment. But sometimes, that object doesn't quite land where it's supposed to. It veers off course ever so slightly, as though something gave it a tiny push that gravity alone can't explain. That push, that extra bit of force, is non-gravitational acceleration. For comets, the usual culprit is outgassing. As comets approach the sun, their surfaces heat up, and volatile materials freeze, turning into gas. This gas escapes, creating a small jet of material that pushes the comet in the opposite direction, just like the way a rocket engine works. It's a weak force, but enough to show up in orbital tracking. Forbes and Butler measured this effect for 3i Atlas. The value they derived was 89, 3 times 10 to the power of -9 astronomical units per day squared. I know this number probably doesn't mean much to you, but let me help you visualize it. Imagine 3i Atlas coasting through space at a constant speed. Every single day, thanks to outgassing, it picks up an additional 13 kilometers per hour in whichever direction the gas is escaping. Doesn't sound like much, does it? 13 kilometers per hour is slower than the average speed you drive on the highway, but in space, even small accelerations add up over time, and in a matter of weeks and months, that tiny push becomes a significant force that cannot be ignored. That might not seem like much. 13 kilometers per hour is a speed slower than your typical highway driving. However, in the boundless expanse of space, where distances stretch beyond our comprehension and time unfolds slowly, even the slightest acceleration over weeks or months leads to immense changes in trajectory deviations that are impossible to ignore. Here's where things take a fascinating turn. The Forbes and Butler paper didn't just record the acceleration, they delved deeper, attempting to unravel the root cause of this strange phenomenon. To do so, they turned to some of the most advanced infrared observations ever made of a comet. Data from the James Webb Space Telescope's cutting-edge SPEC instrument. The JWST has the extraordinary capability to detect the chemical signatures of gases evaporating from a comet's surface. More crucially, it can estimate how much gas is escaping and at what speed, providing unprecedented detail about the comet's behavior. The results they uncovered were startlingly precise. 3I Atlas was losing approximately 150 kilograms of material every second. This gas was escaping at an astonishing velocity of around 1 km. If you've ever seen a rocket launch, you'll know that exhaust velocity plays a pivotal role. The faster the gas is expelled, the more momentum it transfers to the object. So, when you calculate the force of 150 kilograms per second moving at 1 km, it becomes a measurable thrust, a force that directly aligns with the non-gravitational acceleration Forbes and Butler observed. So far, this all aligns with what we know from comet physics. Outgassing creates a tiny but significant thrust. This thrust alters the object's orbit. It's a well-understood principle in comet science, nothing out of the ordinary. A textbook case. But here's the catch. There's a significant issue. And it's not a small one. The amount of acceleration generated by outgassing hinges on two crucial factors: how much gas is escaping and how massive the object is. Think of it like this: a small rocket with a huge engine accelerates quickly, but a massive rocket with the same engine barely moves at all. The same principle applies here. The math behind it is straightforward. Acceleration equals force divided by mass. If you know the force generated by outgassing and you can measure the acceleration, you can deduce the mass. And when Forbes and Butler ran those calculations, they arrived at a mass of just 260 billion kilograms for 3I Atlas. And this is where the paradox deepens. If 3I Atlas truly weighs 260 billion kilograms, then it's tiny, about the size of a 1-kilometer object, assuming comet-like density. This is a far cry from the 5-kilometer giant everyone had been tracking. We're talking about a cosmic pebble in comparison. And here's where it gets even more uncomfortable. The December measurements are internally consistent. The rate of outgassing, the speed at which the gas is escaping, the acceleration measured, and the inferred mass all fit together like a puzzle. The physics checks out. But, and here's the catch, everything we've seen before December doesn't match this. If this object is truly so lightweight, if it can be so easily affected by outgassing, then every previous observation should have seen chaos. Earlier in its orbit, when 3I Atlas was closer to the Sun, the forces of outgassing should have been far more intense. The forces should have been stronger. The trajectory deviations should have been glaring. Impossible to miss. Yet, that's not what they found. For 5 months, hundreds of telescopes tracked 3I Atlas with unparalleled precision, and during all that time, the object moved exactly as gravity predicted. No deviations, no shifts, no signs whatsoever that outgassing had any impact on its path. So, which version of reality do we believe? Is 3I Atlas truly a lightweight object, easily pushed around by the faintest forces, as the December data suggests, or is it the massive, stable giant that seemed impervious to outgassing? As the earlier observations indicated, both datasets exist. Both were gathered by expert teams using state-of-the-art technology. Both have been scrutinized. And yet they present us with two versions of the same object that cannot both be true. This is what a real physics paradox looks like when it slowly creeps up on us. Not a dramatic contradiction that demands immediate attention, but a subtle, creeping realization that the numbers just aren't adding up. Somewhere along the chain of observation, analysis, and interpretation, something has gone catastrophically wrong. And the truly unsettling part, the December paper might not even be the strangest part of this entire mystery. Before Forbes and Butler published their findings, another research team spent 5 long months observing 3I Atlas, meticulously measuring its position with extraordinary precision. They were searching for precisely the type of non-gravitational acceleration that December's paper claims to have found. And what they observed, or rather, what they failed to observe, may very well make this mystery even more perplexing. Part 3. The 5 months where nothing moved. Between March and August of 2025, 3I Atlas was tracked with precision that set a new record for interstellar object observation, not because astronomers expected anything unusual, but precisely because they wanted to rule out any potential anomalies. The team orchestrating this effort was led by Clue and Varys. Their goal was deceptively simple. They wanted to measure 3I Atlas's position with such precision that even the smallest deviation from a purely gravitational orbit would be detectable. This wasn't a casual observation. We're talking about astrometry on the cutting edge of what ground-based telescopes can achieve. The measurements tracked positional changes down to an incredibly precise 0.028 arcseconds. To give you a sense of scale, an arcsecond is an derde, 600 of a degree. It's the width of a dime viewed from about 4 kilometers away. Now, take that precision and divide it by 36. That's what the team achieved: 0.028 arcseconds. It's the equivalent of observing someone placing a coin on the ground 100 kilometers away and being able to determine if they nudged it half a millimeter to the left. Why does this matter? Because when an object is pushed by forces other than gravity, it drifts slowly, steadily, predictably. Outgassing doesn't reveal itself with sudden, dramatic shifts. It manifests as subtle deviations from the expected trajectory, gradual shifts that grow over time as the object falls slightly off its predicted path. The team's observational setup was designed specifically to detect such deviations, and they didn't just observe for a few days. They tracked 3I Atlas continuously for 5 months, building up an orbital solution with hundreds of data points, each one cross-checked and calibrated to minimize error. This wasn't a quick snapshot, it was methodical, exhaustive. The kind of patient observation that transforms uncertainty into hard, irrefutable data. So, what did they find? Nothing. Absolutely nothing. 3I Atlas moved exactly as gravity predicted. Every single observation fell within the noise of the model. No drift. No deviation. No sign of any force other than the gravitational pull of the sun and the planets acting on the object. For 5 months, 3I Atlas coasted through the inner solar system like a ballistic missile, utterly indifferent to the outgassing that should have been shifting it off course. Now, you might be thinking, perhaps the non-gravitational acceleration was just too faint to detect. It's a logical assumption. And yet, there's one glaring issue. The Cloak team didn't just guess their detection limits, they meticulously calculated them. They knew exactly how sensitive their instruments were. According to their analysis, they should have been able to detect non-gravitational forces 300 times weaker than the measurements Forbes and Butler made in December. Read that again, 300 times weaker. If 3I Atlas was experiencing an acceleration of 89, 3 times 10 to the power of -9 astronomical units per day, squared in December, the Cloak team's observations should have revealed it loud and clear in their data. Like a signal flare streaking across the sky. It wouldn't have been subtle. It wouldn't have been a borderline case. It would have been impossible to miss. And yet, they missed it. Or perhaps more accurately, it wasn't there. At this point, you might be thinking, maybe the observations didn't overlap at the right time. Maybe the outgassing didn't begin until after the campaign had concluded. But that's not how comets operate. Outgassing doesn't start like flipping a light switch. It builds up gradually, driven by solar heating, becoming stronger as the comet gets closer to the sun. If anything, outgassing should have been stronger during the Cloak observations when 3I Atlas was closer to the sun. The expected forces should have been more pronounced. The deviations from its predicted path should have been impossible to ignore. But that's not what happened. For 5 months, the observations showed nothing, no signs of outgassing, no visible deviations from the predicted path. The object coasted through the solar system with barely a whisper. How do we explain this? How can an object that was supposed to be reacting to these forces, an object that was closer to the sun during these observations, suddenly exhibit no detectable acceleration for months, and then, only later, show strong, easily measurable acceleration despite being farther from the Sun and presumably less active. This doesn't fit with any normal comet physics. But here's where the paradox deepens. It's not simply a matter of whether outgassing occurred or not. It's about what the absence of motion tells us about the object's inertia. Inertia, that invisible force that resists changes in motion, is intrinsically tied to mass. If 3I Atlas didn't budge for 5 months, even while being heated by the Sun, even while presumably releasing gas, then it was behaving like an object with immense mass, something massive, something that outgassing forces simply couldn't budge. To illustrate, imagine this: if you gently push a beach ball, it rolls. If you push a boulder with the same force, it barely moves. The difference: inertia. More mass means more inertia. And for 5 months, 3I Atlas resisted acceleration exactly as you'd expect from an object weighing 33 trillion kilograms. The orbital data fit this assumption perfectly. But then, in December, everything changed. The same object that had been behaving like a massive, stable entity for months suddenly started to behave as if it weighed just 260 billion kilograms. Same object, same laws of physics. Two completely incompatible inertial responses. Now, I want to be very clear, the Cloak team wasn't wrong. The Forbes and Butler team wasn't wrong either. Both groups followed solid, meticulous methodology, and both conclusions are supported by their respective observations. This isn't a case of sloppy science or bad measurements. No, this is a case of reality refusing to cooperate with our models. And that's what makes it so unsettling. We're not dealing with a simple mistake that can be corrected and forgotten. We're dealing with two highly credible data sets that describe mutually exclusive physical states. One says the object is massive and stable. The other says it's lightweight and reactive. And the gap between these two conclusions is not something you can hand-wave away with measurement uncertainty or varying observational conditions. The evidence is there, staring us in the face. And we are left with a choice. Either something extraordinary happened to 3I Atlas between August and December, something that fundamentally changed its mass, its response to forces, or our understanding of how mass behaves through motion is missing something crucial. Neither option is comforting, because if objects can somehow hide their mass, if they can appear massive in one set of conditions and lightweight in another, then every asteroid we've ever tracked, every comet we've studied, every near-Earth object we rely on for predictable orbits, all of it could be built on assumptions that hold true only sometimes. 3I Atlas isn't just challenging what we know about this one object. It's challenging the reliability of the entire framework we use to infer mass from motion. This framework, older than spaceflight itself, has been tested, trusted, and proven reliable for decades. It's the foundation of how we understand the movement of objects in the cosmos. It's not supposed to fail this spectacularly. So, what happens when it does? What happens when inertia itself stops making sense? Inertia is one of those concepts that seems self-evident until you try to define it. It's why a shopping cart is easy to push when it's empty, but difficult when it's full. It's why you lurch forward when a car suddenly brakes. Inertia is the property of matter that resists changes in motion. It's fundamentally tied to mass. More mass means more inertia. Less mass means less inertia. This isn't just a theory. This is Newtonian mechanics, the bedrock of classical physics. And here's the kicker: you don't need to see mass to measure it. You just need to observe how an object responds to forces. Push on something and watch how it accelerates. The slower it accelerates, the more massive it is. This principle is what allows us to weigh planets, moons, asteroids, and everything in space that we can't physically touch. We apply a known force, typically gravity from a nearby body, and track how the object moves. The math does the rest. For 3I Atlas, astronomers weren't applying direct forces, they were observing how the object coasts through space, noting how external forces, like solar gravity and outgassing, affected its trajectory. And here's where the paradox becomes mathematically vicious. If 3I Atlas really weighed only 260 billion kilograms, then even the tiniest forces should have produced noticeable effects on its trajectory. Solar radiation pressure, the gentle push from sunlight hitting the object's surface, should have nudged it off course. Even weak outgassing should have created orbital residuals, small but measurable differences between where the object was predicted to be and where it actually appeared. But for 5 months, there were no residuals. The orbit fit a purely gravitational model, and every observation was consistent with the idea that the object wasn't being pushed around by anything other than the sun's and planets' gravitational pull. The only way that happens is if the object has enough inertia to resist those small forces. And that requires mass, a lot of mass. Now, you might be wondering, what about brightness? Couldn't the object's albedo reflectivity be throwing off the mass estimate? Absolutely. It could. Brightness depends on size, surface reflectivity, and composition. A small shiny object can look just as bright as a large, dark one. So, when astronomers see a bright dot through their telescope, they can't instantly determine whether they're looking at a small snowball or a large, dark rock. They have to make assumptions, and those assumptions feed into the mass estimate. But here's the critical point: inertia doesn't care about brightness. It doesn't matter if the object is shiny or dull, smooth or rough, rotating or stationary. Inertia is all about how much matter is packed into the object, and you reveal inertia by watching how the object moves when forces act on it. For Tracy Atlas, the Cloak team's 5-month observation campaign provided exactly the test needed to reveal this. Forces were acting on the object. Solar radiation pressure was constant. Outgassing, if it occurred, would have contributed additional force. And the object's response to those forces, or lack thereof, told a clear story. It behaved like something massive until December, when it didn't. But shape doesn't alter inertia. A cigar-shaped object with 260 billion kg of mass still has exactly 260 billion kg of inertia. It still responds to forces in the same way, with the same resistance to acceleration. Now, rotation introduces complexity. An object spinning can exhibit motion that seems more chaotic, particularly if it's outgassing asymmetrically. Jets could fire from different parts of the surface as the object spins, generating forces that, when averaged, might look different than if the object were stationary. However, rotation doesn't hide mass. It just complicates how mass reveals itself. And importantly, the CLI team's observations spanned months, averaging out any rotational effects. If a non-gravitational acceleration signal were hidden in the rotation, it should have emerged in the data, but it didn't. This brings us back to the fundamental equation. Acceleration equals force divided by mass. You measure acceleration by tracking the position over time. You estimate force based on known physics, solar radiation, outgassing, whatever forces are relevant, and then you solve for mass. The Cloak team's data suggests a large mass. The Forbes and Butler data points to something small. Both can't be correct unless one of those 3 variables, acceleration, force, or mass, is behaving in a way we don't yet understand. That's the inertia problem. It's not that we've made a measurement error or misunderstood the forces at play, but that inertia itself, the thing we thought was reliable, consistent, and constant, appears to be context-dependent. It's as if 3I Atlas has one inertial mass when it's coasting through space like a ballistic projectile, and another when it's outgassing near perihelion. Physics doesn't allow that. Inertial mass and gravitational mass are equivalent, a cornerstone of general relativity, one of the most rigorously tested principles in all of science. If an object's resistance to acceleration could change without its gravitational mass changing, we would be violating symmetries that have held firm since Einstein. So, either we've discovered the first exception to that equivalence, which would be a Nobel Prize-level discovery, and almost certainly incorrect, or something else is happening. Something that makes 2 different measurement techniques yield 2 completely different values, because each is capturing a different aspect of a reality we haven't fully mapped yet. This is what paradoxes do. They corner you. They force you to challenge everything you thought was settled. And right now, 3I Atlas has cornered one of our fundamental assumptions that mass is a well-defined property, one that reveals itself consistently regardless of how we measure it. If mass isn't behaving the way we expect, we need to start asking the difficult questions. What if this object isn't a normal comet? What if the standard logic we apply to icy bodies from the Oort cloud doesn't apply to something that formed in another star system, under completely different conditions, with entirely different chemistry? What if our models of how comets lose mass are catastrophically incomplete? Part 5. Why standard comet logic breaks completely. Let's do some simple math, not complicated equations. Just basic arithmetic. We're going to calculate how much mass 3I Atlas would have needed to lose to reconcile the old mass estimate with the new one. 33 trillion kg minus 260 billion kg equals approximately 32. 7 trillion kg. That's how much material would need to have vanished if both measurements are accurate snapshots of the same object, observed at different times. Censura. 7 trillion kg. Sublimated. Ejected. Blown into space, whatever the process is. This is not a rounding error. It's not a slight discrepancy due to observational noise. That's the equivalent of the object shedding 99% of its entire mass. Now, here's the big question. Can a comet lose that much mass so quietly? The answer is no. Absolutely not. Not even close. Comets lose mass all the time. That's their nature. They're made of frozen volatiles, held together by dust and organics. And when sunlight hits them, the ices sublimate directly from solid to gas. This process is gradual, predictable, and well understood. A typical comet might lose millions of kilograms per orbit as it swings past the sun. Some particularly active comets lose billions of kilograms. But 32 trillion kg in a matter of months, without anyone noticing. Let me put that in perspective. When a comet loses that much mass catastrophically, it doesn't just fade away into the background. It fragments. It creates a massive debris cloud. The brightness spikes dramatically as fresh. Pristine ices get exposed to sunlight. The tail, if there is one, brightens and broadens as gas and dust pour off the surface. Ground-based telescopes, space-based observatories, amateur astronomers, even backyard telescopes, all of them would notice. You can't hide that kind of event. It's the astronomical equivalent of a building collapsing. People notice. But no one noticed with 3I Atlas. It didn't fragment. Its brightness didn't spike. There was no debris cloud. No sudden surge in tail activity. No indication whatsoever that the object was disintegrating. It just coasted quiet. Stable. Unremarkable. Exactly what you would expect from a solid, coherent body that wasn't falling apart. So, how do you lose 99% of your mass without appearing to fall apart? You don't. Not if you're a comet. Not if you're playing by the rules. Now, here's where things get chemically complicated. Comets from our solar system, ones that formed in the Oort cloud or the Kuiper belt, have a well-understood composition: water ice, carbon dioxide ice, methane, ammonia, and various organic compounds. We've sent spacecraft to comets. We've analyzed their spectra. We know what they're made of, more or less, and we know how these materials behave when heated. But 3I Atlas didn't form in our solar system. It formed around another star, under completely different conditions, and that means its composition could be radically different from anything we've studied up close. The detection of hydrogen cyanide and its outgassing was already a surprise, not because hydrogen cyanide itself is rare, but because the ratios and abundances didn't quite match what we see in solar system comets. Some researchers have clung to this as a potential explanation. Maybe 3I Atlas is made of unusually volatile ices, substances that sublimate much more aggressively than typical water or carbon dioxide. Perhaps its interior is laced with hypervolatile compounds that don't exist in meaningful quantities in our local comets. And maybe, just maybe, those volatiles could explain the high mass loss rates observed, shedding 32 trillion kilograms in just a few months. But there's a problem with that theory. Volatility explains how fast mass leaves. It doesn't explain where the mass goes. If 3I Atlas was shedding 32 trillion kilograms, that gas and dust would have to go somewhere. It would form a coma, a glowing halo of gas and dust surrounding the nucleus. This would scatter sunlight and show up in spectroscopic observations as emission lines from excited molecules, while 3I Atlas did show some outgassing signatures. They were modest, nothing even close to what we would expect from an object, shedding such a colossal amount of mass that quickly. So, the chemistry doesn't help us. The dirty snowball model, the idea that comets are loosely bound piles of ice and dust, doesn't work here. Neither does invoking exotic interstellar volatiles, because no known sublimation process, no matter how aggressive, it can explain the combination of high mass loss and low visible activity observed in 3I Atlas. And that's before we even consider the structural issue. If an object is shedding 99% of its mass, it's not simply sublimating, it's disintegrating. The internal structure can't hold. You'd witness fragmentation, crumbling, a catastrophic failure. We've seen comets do this before. Shoemaker-Levy 9 shattered into pieces before it impacted Jupiter. Comet Schwarzmann-Wachmann tree fragmented in totus in or 6, splitting into dozens of pieces. These events are dramatic, observable, unmistakable. But 3I Atlas did none of that. It remained intact, coherent, and stable. So, we're left with a mystery that standard comet physics can't resolve. The object didn't shrink the way comets typically shrink. It didn't break apart the way comets break apart. It didn't brighten or fragment. Nor did it leave behind a trail of debris that would signal catastrophic mass loss. Yet, somehow, it transitioned from behaving like a 33 trillion kg giant to acting like a 260 billion kg lightweight. This is where the paradox shifts from being a measurement problem to a physics problem. Because now we've ruled out the most obvious explanations. This isn't a data mistake. It's not a misunderstanding of comet composition. It's not simply a case of unusual but natural sublimation. The numbers don't align with any known framework for how icy bodies lose mass. This forces a question we're hesitant to ask. What if 3I Atlas isn't behaving like a comet because it isn't one? What if we've been trying to force this object into a category it was never meant to fit? And the paradox exists because the assumptions underpinning that category simply don't apply. That's not evidence of anything exotic. It's not proof of artificiality, alien engineering, or any of the sensational theories that swirl around interstellar objects. But it is evidence that our models are incomplete. There are objects out there, maybe rare, maybe not, that don't follow the rules we've spent centuries establishing. And 3I Atlas, whatever it is, has just become Exhibit A in the case that the universe is stranger than our textbooks admit. So, if normal comet logic doesn't work, what kind of explanation could reconcile 5 months of massive stable behavior with December's lightweight acceleration? That's where the rescue attempts begin. And some of them are surprisingly clever right up until you realize how many coincidences they require to make sense. Part 6, Vector Cancellation. The Jet Geometry Escape Hatch. Picture this. You're standing on a skateboard, holding a fire extinguisher. You point it forward and pull the trigger. Foam jets out, and Newton's third law kicks in. You roll backward. Now, imagine you have 2 fire extinguishers, one in each hand, pointing in opposite directions. You pull both triggers simultaneously. The forces cancel each other out. You don't move. This is the basic principle behind vector cancellation. It's one of the more elegant ways to potentially resolve the 3I Atlas paradox without invoking anything truly exotic. The logic goes like this. What if the object was outgassing during the cloak observations, but the jets were oriented in such a way that their forces cancelled out? What if multiple active regions on the surface were firing in opposite directions, producing thrust that, when averaged over time, cancelled out? It's not a crazy idea. Comets aren't perfect spheres, and outgassing doesn't occur uniformly. The surface is a patchwork of icy regions, rocky patches, and volatile rich deposits. As the object rotates and different parts face the sun, jets activate and deactivate in complex patterns. If you have one jet firing from the northern hemisphere and another from the southern, pointing in roughly opposite directions, their forces could theoretically cancel each other out. But here's where the geometry starts to get uncomfortable. For cancellation to completely hide the acceleration signal, the jets need to be almost perfectly opposed, not just roughly opposite, but perfectly balanced, to within the sensitivity of the cloak team's observations. And remember, they could detect forces 300 times weaker than what Forbes and Butler measured in December. That means even the slightest imbalance in the jet forces would have shown up. And it's not just about the directions, the timing is crucial too. Comets rotate, and as they spin, jets sweep across the sky like cosmic sprinklers, changing their orientation continuously. For cancellation to work over 5 months of observations, the rotation axis, the locations of active regions, and the outgassing rates would have to align in a very specific way. The thrust vectors would need to average out to zero, not just at one moment, but across hundreds of observations taken at different times from different angles. Is that possible? Sure. But how likely is it? The real issue arises when you ask why the cancellation would suddenly stop working in December. If the jets were balanced during the cloak campaign, something would need to change in order to unbalance them later. Maybe one region ran out of volatiles. Perhaps thermal conditions shifted as the object moved farther from the sun. Or maybe the rotation state evolved in a way that altered the average thrust vector. This is where thermal precession enters the picture. Thermal precession is a real phenomenon, where outgassing forces not only push the object but also gradually torque it, changing its spin axis over time. If 3I Atlas's rotation axis shifted between August and December, that could have broken the symmetry that kept the jets balanced. What was once a cancelling configuration could suddenly become an accelerating one, and boom, you get the December signal. It's clever. It's physically plausible. It doesn't require new physics or exotic materials, just geometry, timing, and a bit of thermal evolution. But let me ask you this. How many interstellar objects have we observed closely enough to test this hypothesis? 2. Oumuamua and 3I Atlas. That's it. We have exactly 2 data points for how objects from other star systems behave when they pass through ours. If the explanation for why 3I Atlas looks so strange is that the jets just happened to cancel perfectly for 5 months and then stopped cancelling right when JWST was watching, we're leaning heavily on coincidence. Coincidences aren't impossible. Nature doesn't owe us simple explanations. But when you start stacking low-probability events, perfect jet alignment, precise rotational phasing, and thermal evolution kicking in exactly when we need it to, you're building a house of cards. Each individual card is solid. The physics checks out. But the whole structure relies on everything happening just so. And that's before we address the deeper question. If vector cancellation is common enough to explain 3I Atlas, why didn't we see it with Oumuamua? Oumuamua also exhibited non-gravitational acceleration, but no one invoked cancellation there, because the signal was clean, persistent, and didn't require elaborate geometric explanations. So either 3I Atlas is uniquely unlucky, or vector cancellation is being asked to do more explanatory work than it can reasonably handle. None of this rules out the hypothesis. It's a legitimate possibility, and researchers are taking it seriously, but it's not the slam-dunk resolution that some headlines might suggest. It's a potential piece of the puzzle, and it works best when combined with other ideas, like the possibility that the object's thermal behavior is more complicated than we thought. Which brings us to thermal lag, another clever escape hatch that might explain why December was different from everything that came before. Part 7, Eubank's thermal time lag model. Heat doesn't move instantly. If you put a frozen turkey in the oven, the surface cooks long before the center thaws. That's thermal lag, and it's a crucial concept for understanding how comets respond to solar heating. When sunlight hits a comet's surface, the outer layers absorb energy and warm up quickly, but the interior stays cold for a long time. Heat has to diffuse inward through ice, rock, and porous voids. and that process is slow. Marshall Eubanks, a researcher who has spent years modeling the thermal behavior of small bodies, proposed that thermal lag might explain why 3I Atlas seemed dormant for months and then suddenly became active. The idea is simple, but powerful. During the early part of its solar passage, only the surface layers of 3I Atlas were warm enough to outgas. The deeper, volatile-rich regions, the ones that could drive significant mass loss and non-gravitational acceleration, were still frozen solid. The outgassing was weak, localized, and possibly symmetrical enough that it didn't produce a detectable acceleration signal. But as weeks turned into months, heat kept diffusing inward. Slowly, thermal energy reached pockets of volatiles buried beneath the surface. And when those pockets finally hit sublimation temperature, they activated not all at once, but progressively as the thermal wave propagated through the object's interior. By December, enough of these deeper regions had activated, and the outgassing rate spiked, driving the strong non-gravitational acceleration measured by Forbes and Butler. This model has a lot going for it. It's based on real, well-timed physics. We know that comets are porous and conduct heat slowly. We know that subsurface ice can remain stable even while surface ice sublimates. And we know that comet activity often increases as objects approach perihelion, not because they're getting closer to the sun in a simple, linear way, but because thermal diffusion is finally catching up. The December timing perfectly aligns with this theory. 3I Atlas reached its perihelion, the point in its orbit where it was closest to the sun in mid-2025. If thermal lag operates on timescales of weeks to months, then December is precisely when you'd expect delayed activation to kick in. For months, the surface had been absorbing solar energy. And finally, that energy penetrated deep enough to liberate the buried volatiles, resulting in a sudden burst of outgassing powerful enough to produce measurable thrust. So, does this fully resolve the paradox? Does thermal lag explain why the cloak observations saw nothing, and Forbes and Butler saw everything so clearly in December? Maybe. Here's what this model does well. It accounts for the timing. It explains why outgassing might suddenly ramp up instead of following a smooth curve tied solely to solar proximity. It offers an explanation for why earlier observations could have missed a subtle signal that later became much more apparent. This makes sense. It's plausible, and it's grounded in the solid science of comet behavior. But here's where it falls short: inertia. Even if the outgassing was weak during the cloak observations, it should still have been detectable, and if the object truly weighs only 260 billion kg, even weak outgassing should have been enough to produce detectable acceleration. The cloak team's sensitivity threshold wasn't minuscule. They could have seen forces 300 times smaller than the December measurement. If 3I Atlas really is as lightweight as its December mass suggests, thermal lag doesn't hide its response to outgassing. It merely delays when the outgassing becomes intense. Imagine it like this. Thermal lag explains why a rocket engine might ignite late, but it doesn't explain why the rocket behaved as though it had a full tank of fuel before the engine ever turned on. If 3I Atlas truly weighs 260 billion kg, it should have been wobbling, drifting, responding to tiny gravitational perturbations throughout its passage. Thermal lag can delay strong acceleration, but it can't make an object behave like it's 100 times more massive than it actually is. Unless, of course, the mass estimate itself is wrong. Unless the December mass of 260 billion kg is an underestimate due to faulty assumptions about its density or structure, this is where the model starts doing some heavy lifting. If you assume the object is denser than typical comets, the inferred size shrinks, the inferred mass increases, and suddenly, the gap between the two datasets starts to narrow. But now you're stacking assumptions: thermal lag, unusual density, delayed activation, and the right jet geometry to avoid cancellation during early observations. Each of these assumptions individually is reasonable, but together they start to feel like a coordinated effort to force the data into compliance. None of this makes Eubanks's model incorrect. It's a valuable piece of the puzzle and addresses part of the mystery, but it doesn't provide a complete solution. It's like a pressure relief valve, reducing the tension but not fully resolving it. And that's the pattern we see across all proposed explanations. Each one contributes a little piece to the puzzle, but none of them work entirely on their own, which means if we're going to solve this enigma, we need to dig deeper and question assumptions that go even further back, like the assumption that we truly understand what interstellar comets are made of and how dense they should be. Part 8, density, is doing a lot of unpaid labor here. When astronomers estimate the mass of an object they can't physically visit, they rely on a chain of inferences. First, they measure brightness. Then, they estimate size by assuming certain reflectivity or albedo. After that, they calculate volume based on the assumed shape. Finally, they multiply the volume by an assumed density to calculate the mass. Notice how many times the word assumed comes up in that sentence. For cometatlas, the assumed density is roughly 500 kilograms per cubic meter. This number is drawn from studies of comets in our solar system, objects from the Kuiper belt and Oort cloud that we've observed extensively and, in some cases, visited with spacecraft. These solar system comets are typically porous, fluffy, held together by weak gravity rather than structural strength. A density of 500 kilograms per cubic meter is less dense than water, which makes sense if you imagine a loosely packed mixture of ice, dust, and voids. But here's the catch. 3I Atlas didn't form in our solar system. It didn't come from the Kuiper belt or the Oort cloud. It formed around a different star in a different protoplanetary disk, under completely different conditions, and we have no idea what that means for its density. What if interstellar comets are systematically denser than solar system comets? What if the processes that form comets in other stellar environments result in more compact, less porous objects? If the density were, say, 0 kilograms per cubic meter instead of 500, the same volume would correspond to twice the mass. If the density were 1, woo-by, you'd triple the mass. Suddenly, the gap between the old estimate and the new estimate starts to shrink. Let's run the numbers. If you assume the outgassing measurements from Forbes and Butler are correct, and you work backward to infer mass, you get 260 billion kg based on a certain size and density. But if the object is denser than assumed, the size required to produce that mass shrinks. And if the size is smaller but the brightness remains the same, that means the albedo, or reflectivity, must be higher shiny ice rather than dark dust. Suddenly, you're revising multiple assumptions at once, and the inferred properties start to shift. On the other hand, the old estimate of 33 trillion kg assumed a density of 500 kilograms per cubic meter and a certain size based on brightness. If the density is actually higher, the object could be smaller than 5 kilometers, but still massive enough to resist outgassing forces in the way the observations suggest. So, perhaps both teams are right, and the real object lies somewhere in between, not as massive as 33 trillion kg, but not as lightweight as 260 billion either. Perhaps it weighs a few trillion kg, dense enough to shrug off weak outgassing forces, yet light enough to show measurable acceleration when the outgassing strengthens. It's a comforting thought, a middle ground where no one is completely wrong, just slightly imprecise. But there's a problem. Even if you adjust for density, even if you assume the most favorable combination of size, albedo, and composition, you still can't fully close the gap. The December acceleration signal is too strong to dismiss with density adjustments alone. And the cloak non-detection is too clean to dismiss with the excuse that they were just barely below the threshold. Density helps. It narrows the range of possibilities, but it doesn't erase the paradox. It just moves the goalposts closer together. And then there's the deeper issue. We're using density to reconcile the datasets. But density itself is an unknown. We're solving for it indirectly, inferring it from other inferences, each of which carries its own uncertainty. This is what statisticians call uncertainty stacking. When every step in a calculation introduces error, those errors compound as you move through the chain. By the time you reach the final answer, The uncertainty bars are so wide that almost anything becomes plausible, which sounds like flexibility, but it's actually a warning sign. When a model can explain anything, it risks explaining nothing. You need constraints, hard data that pin down at least one variable so the others can't drift arbitrarily. For Tracy Atlas, we don't have that yet. We don't have a density measurement. We don't have a direct size measurement. We don't even have a shape model beyond probably elongated. Everything is inferred. And every inference depends on assumptions that may or may not hold for an object we've never seen up close. So, yes, density could be part of the answer, but invoking it doesn't solve the problem. It just highlights how little we actually know and how much of our confidence rests on extrapolating from solar system objects to something that might be fundamentally different. And speaking of things we don't know, there's another layer to this story that complicates everything further. While scientists were debating mass, density, and outgassing, the orbital models themselves were shifting beneath their feet. Part 9, JPL's quiet revisions and the moving target problem. If you've ever tried to pin down the exact orbit of an asteroid or a comet, you'll know that nothing is ever set in stone. The numbers don't stay static, even if you're sure of your calculations. They shift not in dramatic leaps, but in subtle, constant movements. Every new observation adds data. Every new data point refines the model. And what seemed certain just a month ago now comes with a layer of uncertainty. This process isn't a flaw, it's the heart of scientific inquiry. It's how we build our understanding. It starts with an estimate, an educated guess based on the information at hand. You collect more data, and gradually, the picture becomes clearer. For Tracy Atlas, the central system that tracks these updates is JPL Horizons, a database maintained by NASA's Jet Propulsion Laboratory. Horizons is the key resource for astronomers, offering crucial information about where solar system objects are, have been, or will be in the future. The Horizons database is regularly updated as new observations come in, and as more data refines our orbital models. But not all updates are simply minor tweaks. Sometimes, these updates involve major revisions, altering fundamental assumptions, and setting off a cascade of changes throughout the entire calculation process. That's what's been happening with 3I Atlas. When 3I Atlas was first observed, the orbital model was provisional. That means there was enough data to track the object's movement, but not enough to be confident in all the finer details. Provisional models are fine for short-term predictions like where an object will be tomorrow or next week, but they carry larger uncertainties than mature, well-constrained models that come with years of data. One of the parameters that often carries the most uncertainty in these provisional models is non-gravitational acceleration. Early on, JPL's models included a modest non-gravitational term, something on the order of a few times 10 to the power of -9 astronomical units per day squared, not zero, but not large either. It was a minor factor, but enough to influence the overall picture. As more data poured in, that value shifted. Sometimes it increased, other times it decreased. The error bars got wider. The point estimates moved. Here's the issue when you use those orbital parameters to infer mass, as Forbes and Butler did. You're essentially building your conclusions on a foundation that is still in motion. If the value for non-gravitational acceleration shifts after your paper is published, it alters your mass estimate not because your analysis was wrong, but because the data has evolved. This is the moving target problem. You're trying to hit a bullseye, but the target keeps shifting. And in the case of 3I Atlas, where the mass estimate depends heavily on the exact value of acceleration, even the smallest changes in the orbital model can lead to large changes in the inferred mass. JPL doesn't make a public spectacle every time they tweak an orbital parameter. They don't hold press conferences. They quietly update their database, and researchers who are paying close attention adjust their conclusions accordingly. But for the broader public journalists, science communicators, even the general audience, the narrative gets frozen at the last published headline, creating a kind of narrative lock-in. Once a number enters the public discourse, It's incredibly difficult to dislodge. 3. I, Atlas, lost 99% of its mass, makes for a sensational headline. It's dramatic, memorable, and shareable. But if the actual discrepancy turns out to be smaller because the orbital parameters have shifted, or the mass estimates converge to a middle ground, those corrections don't attract the same attention. This isn't unique to 3i Atlas. It happens all the time in science. Early results get amplified, while later revisions often get ignored. The public ends up with outdated or incomplete understandings because the correction loop never quite closes. But here's where the issue goes beyond just data, it's philosophical. Science doesn't give you certainty, it offers the best current estimate, accompanied by error bars, and the willingness to update when new data arrives. That process is messy, frustrating, and it's how we move closer to the truth. With 3i Atlas, we're still in the midst of that process. The Forbes and Butler paper is a snapshot in time, not the final word. The cloak observations provide valuable constraints, but they don't close the case. JPL's orbital model is still evolving, not yet settled. The mass paradox might resolve itself as data sets improve and assumptions become more precise, or it might not, because there's a point where further improvements in the data don't eliminate the tension. They just sharpen it. When that happens, when you've resolved all the uncertainties, and the paradox is still there, that's when you start questioning whether the issue lies with the data or with the framework itself. 3 Atlas might be pushing us toward that threshold, and if it is, we must start thinking seriously about what happens when natural explanations require too many coincidences. Part 10. When natural explanations start requiring coincidences. Let's take stock of what we need to explain. To account for why 3i Atlas behaved like a massive object for 5 months and then suddenly became lightweight in December, we need a set of conditions to be true simultaneously. First, the outgassing jets need to have been geometrically aligned during the cloak observations in such a way that their forces cancelled not approximately, but precisely, within the sensitivity of the measurement. Second, thermal lag needs to have delayed the activation of subsurface volatiles, but exactly until the right moment, late enough to have been missed by the cloak campaign, but early enough for JWST to catch it. Third, the object's density needs to be higher than typical comets, but not so high that it contradicts the spectroscopic data suggesting it's made of icy material. Fourth, the shape and rotation state need to cooperate, producing a brightness profile and light curve that match the observations without introducing contradictions. Fifth, everything must line up timing-wise. The thermal evolution, rotational precession, and jet activation need to follow the right sequence and happen at just the right moments. Individually, each of these conditions is plausible. None of them defies known physics, but together, they require a level of coordination that starts to feel less like an explanation and more like a sequence of convenient justifications. This is what we call inflating epicycles. The term comes from ancient astronomy when scholars tried to explain planetary motions with Earth-centered models. To fit the observations, they added epicycles, smaller circles within the circles. Each one was mathematically valid. Each one explained a specific discrepancy, but the system grew so complex it became untenable. We're not at that point yet with 3i Atlas, but we're getting close. Each new hypothesis adds another layer of coincidence, another just-so condition that must be satisfied to make the entire explanation hold together. And here's the uncomfortable question: if nature works like this, if everything depends on so many unlikely alignments and timing, why don't we see this more often? We've observed thousands of comets. We've tracked dozens of near-Earth asteroids with precision comparable to the Cloak campaign. We've studied outgassing, thermal lag, jet dynamics, and rotational evolution. Yet 3i Atlas is the first object to exhibit this paradox so spectacularly. That's statistically strange. Not impossible, but strange. If the explanation relies on stacking 5 or 6 low-probability events, and we have only 2 interstellar objects to compare, then either 3i Atlas is extraordinarily unlucky, or the explanation isn't capturing the full picture. This reminds us of past anomalies. Mercury's orbit once didn't fit the predictions of Newtonian gravity. For decades, astronomers proposed increasingly elaborate solutions. Maybe there was an undiscovered planet inside Mercury's orbit. Maybe the sun was slightly warped. Or maybe gravity worked differently at small distances. All plausible. All wrong. The real answer, general relativity, a paradigm shift nobody saw coming until Einstein unveiled it. I'm not suggesting 3I, Atlas needs a new theory of gravity that would be absurd. But I am saying that when natural explanations require this many coincidences to make sense, we must step back and consider whether we're solving the right problem. Here's a possibility that no one likes to talk about openly. It's speculative. It invites sensational headlines. And it stirs up conspiracy theories. But it remains a possibility. What if 3I Atlas isn't behaving like a natural object because it isn't one? This isn't proof. It isn't evidence. This question lurks at the edge of the conversation, one that scientists think about privately but rarely speak of publicly. Suggesting artificiality brings you to a place where science struggles to test or constrain the idea. It's not easily dismissed, either, but ignoring it doesn't make it go away. As we'll explore next, there are uncomfortable reasons why this hypothesis keeps resurfacing. Part 11, JWST's Quiet Revolution in Small Body Physics. But as is often the case with groundbreaking instruments, the James Webb Space Telescope, JWST, is revealing things we never expected. And one of the most intriguing discoveries is that small bodies in our solar system are far stranger than we could have ever imagined. Since its launch in late 2021 and the start of its scientific operations in 2022, JWST has been casting its powerful infrared gaze toward asteroids, comets, and other minor celestial bodies whenever scheduling permits. What it has uncovered is a pattern of anomalies, a pattern not in the sense of physics breaking down, but in terms of violations of the assumptions that astronomers had built over decades of observation. We're talking about unexpected chemistry, thermal signatures that refuse to align with models, outgassing rates that surge and diminish in ways that simple sublimation fails to explain. It's a cascade of revelations that challenge the very frameworks we've relied on. JWST's sensitivity is so high that it's uncovering molecules and compounds that were previously invisible to ground-based telescopes. And when you detect something unexpected, you can't simply ignore it. You have to revise the model. That process of rethinking extends beyond a single object. And suddenly, you're left questioning whether the models we've applied to all objects, to everything we've studied, might have been wrong from the very beginning. 3I Atlas fits this trend perfectly. The detection of hydrogen cyanide, the unusual outgassing patterns, the puzzling mismatch between the object's brightness and its inferred composition, these are not outliers reserved for just interstellar objects. These discoveries belong to a wider phenomenon where JWST continually finds small bodies that refuse to follow the well-worn paths we've written for them. This isn't just about better technology. It's a conceptual shift in our understanding. With improved instruments, we can see things we couldn't before. And what we see often complicates our understanding of the cosmos. That's a form of progress, even if it feels chaotic at times. But there's a deeper issue here, one that stretches back to the core of our models. Our understanding of comets, asteroids, and other small bodies has been shaped by the brightest, the most active, the most visible objects, those that shine the most and are the easiest to observe. The problem is that we have generalized from the exceptional to the typical, and now we're realizing that the term typical may not mean what we thought it did. The discovery of interstellar objects like 3I Atlas intensifies this issue. We have no prior experience with comets that have formed around a different star. We don't know what the volatility, thermal properties, or structural characteristics of these objects should be. Every assumption we've borrowed from solar system studies might be flawed. Without sending a spacecraft to intercept one of these objects, an endeavor that is decades away from reality, we have no real way of testing these assumptions. So, when 3I Atlas arrives and behaves strangely, we can't simply say, well, most interstellar comets do this, so it must be fine. After all, we have one other data point, Oumuamua, which was even more bizarre. No outgassing detected at all. Despite exhibiting non-gravitational acceleration, its shape was like nothing we had ever seen, and it was gone before any follow-up could be performed. Two objects. Two paradoxes. Maybe that's a coincidence. Maybe interstellar space is simply full of strange objects, and we are witnessing the diversity of bodies that formed under vastly different conditions. But maybe this is also a signal that our detection methods, our interpretations, and the assumptions we've been relying on are fundamentally biased toward finding things that fit our expectations. And when something doesn't fit, we simply don't know how to classify it. JWST is exposing that bias. It's showing us that the small body population these comets, asteroids, and interstellar visitors is far more diverse, more chemically complex, and more dynamically active than we ever realized. And sitting at the extreme edge of this diversity, 3I, Atlas, is forcing us to ask, where does the natural diversity end? And where does genuine anomaly begin? Because there's a critical difference between saying, this object is unusual and this object is impossible. Unusual, we can handle that. Unusual just means our models need updating, that the edges of our understanding need expanding. But impossible means the rules are broken. And when the rules appear to be broken, you're left with two options: rewrite the rules, or consider that maybe the object isn't following them because it was designed not to. And that brings us uncomfortably, reluctantly back to the hypothesis that simply refuses to die. Part 12, non-gravitational forces are suddenly everywhere. For most of the 20th century, astronomers assumed that when calculating the orbit of an asteroid or a comet, gravity was the only force that mattered. The sun pulled, the planets pulled, and the object followed a predictable, well-understood trajectory. Simple, elegant, deterministic. But then, as our instruments improved and precision increased, astronomers began noticing discrepancies, small ones at first, but significant when examined closely. Objects weren't always where they were supposed to be. The deviations were tiny, almost imperceptible, but real nonetheless. As researchers dug deeper into the data, they uncovered that small forces, once thought to be negligible, were actually having a significant impact. Solar radiation pressure was one of them. Sunlight carries momentum, and when it reflects off an object's surface, it imparts a tiny push. For a large asteroid, this is inconsequential, but for a smaller one, especially if it's reflective, the push adds up over time and shifts the orbit measurably. Outgassing is another force we hadn't fully accounted for. Every time a volatile substance on a comet sublimates and jets away, it's like firing a miniature rocket engine. And when that outgassing is asymmetric, when more gas escapes from one side than the other, the object gets a net push in that direction. The Yarkovsky effect is a third example. Subtle, but real. As an asteroid rotates, the sun heats one side. As that side rotates away and cools, it radiates heat. The result is a small force that, over millions of years, can significantly alter the object's orbit. These forces were always there, present in the universe. They didn't suddenly emerge when we started measuring them with better precision, but for decades, they were too small to detect reliably. Now, with modern astrometry and decades of accumulated observations, they're no longer hidden in the noise. They've become essential. If you ignore these non-gravitational forces when modeling the orbits of small bodies, your predictions will be fundamentally flawed. These forces have always been part of the cosmic landscape, lurking in the background. They didn't suddenly materialize when we began measuring them more precisely. However, for a long time, they were buried beneath the noise floor, too subtle to detect reliably. Now, with the cutting-edge precision of modern astrometry and decades of accumulated data, they are no longer hidden. In fact, they've become absolutely essential. Ignoring these non-gravitational forces when modeling the orbits of small bodies is no longer an option. Doing so will lead to fundamentally flawed predictions. And here's where the complexity deepens the smaller and lighter the object, the more crucial these forces become. For a massive asteroid like Ceres, the impact of non-gravitational forces is negligible, almost non-existent. but for a lighter, more delicate object, like a comet nucleus. Non-gravitational forces can completely reshape its orbit. For an object like 3I Atlas, if the December data truly reflects its lightweight nature, these forces become the primary drivers of its trajectory, overtaking gravity itself. This represents a paradigm shift in how we think about the forces that shape the orbits of small bodies. What we once considered merely corrective factors have now become foundational to our understanding of their movement. This shift doesn't just change how we model comets and asteroids, it has profound implications for space navigation and planetary defense as well. If we can't reliably account for these forces, how can we predict where an object will be in the future, and if that object is on a collision course with Earth? This is more than a theoretical problem, it's a real danger. 3I Atlas sits squarely at the edge of this new understanding. A test case that pushes us to rethink the rules. The non-gravitational acceleration measured by Forbes and Butler isn't just noticeable, it's colossal. Especially when compared to most objects in our solar system, it's a warning signal, showing us that some small bodies are so sensitive to external forces that we must completely abandon the old, simplistic models we've relied on for centuries. We can no longer afford to ignore these complexities. But here's the catch: while non-gravitational forces are critical, they are notoriously difficult to predict. They depend on so many variables: surface properties, composition, rotation, thermal conductivity, all of which are largely unknown to us and cannot be directly measured from afar. What this means is that when we try to model these forces, we end up with equations that contain dozens of free parameters, variables that can be adjusted at will. And when we fit these models to data, we risk overfitting, crafting a model so flexible that it can explain anything, but predict nothing. This is a dangerous pitfall, because if a model can fit both the non-detection data from the Chloe team and the detection data from December simply by adjusting a few parameters, then we've done nothing to resolve the paradox. We've merely papered over the issue, leaving the problem unsolved. And that's where 3I Atlas becomes more than just an anomaly in the data. It becomes a litmus test for the robustness of our growing understanding of non-gravitational forces. Is it truly a breakthrough? Or is it just flexible enough to accommodate contradictions? And let's be honest, we still don't know. The jury is still out, and the uncertainty is palpable. But as we wait for a definitive answer, there's another, quieter conversation taking place in the background, one that, reluctantly and uncomfortably, revisits hypotheses many would prefer to avoid. Part 13. The return of the artificial hypothesis. Let me make something crystal clear: what I'm about to discuss is pure speculation. It is not a conclusion. It is not supported by definitive evidence. It's simply a hypothesis, one that has surfaced in the scientific conversation not because anyone wants it to be true, but because the data refuses to be neatly dismissed. And in the case of 3I Atlas, the refusal to rule out this hypothesis has become increasingly difficult to ignore. Back in 2017, the first confirmed interstellar object to pass through our solar system, Oumuamua, made waves. From the start, it was odd. Its elongated, possibly tumbling shape, and the brightness curve it exhibited didn't match any asteroid or comet we'd ever seen. The shape alone was bizarre, a strange hybrid somewhere between a cigar and a pancake, with an aspect ratio so extreme it pushed the boundaries of what we thought was possible for natural bodies. Elongated objects weren't new to astronomers, but nothing like this had ever been observed. And then came the kicker: Oumuamua exhibited non-gravitational acceleration, but without any visible outgassing. No coma, no tail, no spectroscopic signatures of escaping gas. Yet it was accelerating. The implications were immediate and unsettling. If an object is accelerating without any visible propulsion, where is the force coming from? The natural explanations began to stretch thin. Perhaps it was emitting hydrogen, an invisible gas that most telescopes struggle to detect because it doesn't produce strong emission lines in the typical wavelengths we observe. Maybe it was a nitrogen iceberg, sublimating in ways that didn't create detectable signatures. Or maybe it was shaped like a sail, exploiting its unique geometry to catch solar radiation and accelerate in a way that a spherical object could never manage. Each explanation worked mathematically. Each could be made to fit the data if you tweaked the parameters just right. But each of them felt like special pleading, like bending the rules to fit something that simply didn't want to conform. That's when Avi Loeb, chair of Harvard's astronomy department at the time, proposed an idea that turned heads. What if Oumuamua wasn't a natural object at all? What if it was a light sail, a thin, artificial structure designed to capture solar radiation and accelerate in space? His paper was careful, hedged with caveats, suggesting this as a low probability possibility, worth considering in the absence of any compelling natural explanation. Loeb wasn't claiming proof. He was asking whether this hypothesis should at least be put on the table alongside the others, evaluated objectively, and tested against future observations. The media response, however, was far from measured. Headlines screamed about alien spacecraft. Talk shows fueled speculation about who might have built it and why it was sent toward us. Loeb became a polarizing figure overnight, praised by some for his scientific courage, criticized by others for reckless speculation that only fueled conspiracy theories. Most astronomers distanced themselves from the artificial hypothesis, not because they could prove it wrong, but because it was, at the time, untestable. Science thrives on hypotheses that can be confirmed or falsified through observation, but artificiality without direct investigation offers neither. The controversy eventually faded, and Oumuamua continued its journey beyond our solar system. Too faint to track and too far to intercept, we moved on. Then came Dry Atlas. Fast forward to 2025. Different object, different behavior, but some of the patterns are eerily similar. For months, it exhibited ballistic motion, with no outgassing detected. The campaign tracked it with incredible precision, searching for any hint of non-gravitational forces, and found none. It moved exactly as Newtonian gravity predicted, stable and passive, like a rock falling through the void of space. Then, suddenly, near perihelion, the object exhibited activity, acceleration, forces that weren't there before, or at least weren't detectable before. It's the same sequence. Passive, then active, dormant, then propulsive, ballistic flight, followed by powered flight, if you want to borrow the terminology of spacecraft. While the natural explanations for 3I Atlas seem more plausible than for Oumuamua after all, comets do outgas, thermal lag is real, and delayed activation makes sense. The fact that we're seeing this pattern again is deeply statistically uncomfortable. 2 interstellar objects, 2 paradoxes, and 2 cases where the simplest natural explanations require an array of coincidences to align perfectly. Oumuamua needed invisible outgassing, exotic composition, or fortuitous geometry. 3I Atlas requires perfect jet cancellation, precise thermal timing, unusual density, and cooperative rotation. Each individual hypothesis is defensible, but together they begin to feel more like an elaborate post hoc rationalization than predictive understanding. Each hypothesis we entertain stands on its own, defensible within the boundaries of reason. However, when we put them together, they start to resemble a patchwork, a form of post hoc rationalization rather than a coherent, predictive framework. I must reiterate, this doesn't imply that 3I Atlas is artificial. The default approach in science, whenever we encounter an unexplained phenomenon, should always be to consider that we are missing some natural explanation, not to leap straight into the realm of artificiality. Nature is vast, full of complexities and surprises, and humans, despite our greatest achievements, are notoriously poor at recognizing the limits of our own understanding. We've been wrong before. Continental drift once seemed implausible until it wasn't. The concept of quantum mechanics seemed absurd until rigorous experiments confirmed its strange truths. The universe, with its infinite quirks, has repeatedly shown that it defies our most intuitive models. But the persistence of this hypothesis, the idea that something might be artificial, isn't driven by scientists' secret desires for alien probes to exist. It arises because, quite simply, we can't definitively rule it out. Absence of evidence is not evidence of absence. Until we can, it remains a logical possibility, however remote, and more importantly, the continuing mystery surrounding interstellar objects forces us to ask a deeper question: are our frameworks truly as universal as we think? The issue here is that artificiality is unfalsifiable. Without a direct investigation, we can't prove that an object is natural simply by looking at it through a telescope. We can only show that the natural explanations available are sufficient up to a point. But when those natural explanations require stacking 5 or 6 improbable coincidences to hold together, the idea of sufficient starts to feel like a fragile construct. It begins to resemble the astronomical equivalent of claiming that, sure, lightning could have struck in exactly this pattern by pure chance, but maybe we should consider whether someone was experimenting with electricity. This is precisely why researchers, even when entertaining such a possibility, to avoid bringing it into the public discussion, it doesn't lend itself to fruitful scientific discourse. You can't design an experiment to test the hypothesis of artificiality without direct interaction with the object. For cometatlas, such a test is simply impossible. It's too far away, too fast. There's no way to gather data that would allow us to make predictions capable of distinguishing artificial behavior from natural. We don't even know what artificial behavior might look like. It's a dead-end conversation, at least for now. Mentioning it publicly, especially without the right data, invites ridicule, fuels pseudoscience, and distracts from the productive work of refining our models and collecting more data. But it serves as a mirror, too. When scientists even reluctantly start invoking the possibility of artificiality, it's often a sign that we've hit a limit with our current understanding. It suggests we are facing something our frameworks simply weren't built to handle, that our tried-and-true tools, brightness measurements, orbital mechanics, spectroscopic analysis, are revealing cracks we didn't anticipate. Whether the answer ends up pointing toward exotic physics or something far stranger, the core issue remains the same. We don't fully understand what we're observing. We're inferring properties from light and trajectories, building models based on assumptions drawn from objects we've studied up close, and hoping those assumptions will hold when applied to visitors from other star systems. But when those assumptions fail, when paradoxes multiply rather than resolve, we are confronted with the uncomfortable reality that perhaps our sample size of one solar system has left us inadequately prepared for the diversity that exists beyond it. 3. Atlas might just be a comet with unusual thermal properties, one that has bad timing for the data we've collected. It could be an object whose internal structure doesn't align with our assumptions of uniform density. It might be composed of materials we've never encountered before, reacting to the forces of space in ways that our current models don't capture. All of these are natural possibilities, and any one of them could be the right answer. But there's also a chance that it's something much stranger, something that doesn't fit neatly into our pre-existing categories of comet or asteroid, simply because those categories were defined by objects that share a common origin in our protosolar nebula. Perhaps 3I Atlas is a cosmic traveler from another star system, challenging not just our measurements, but the very assumptions we've built about what kinds of objects can and do travel through interstellar space, and why they do so. Either way, its very existence is forcing us to reckon with gaps in our knowledge, gaps that won't close until we reconsider our approach to structure, composition, and the possibility that mass itself doesn't reveal itself as simply as we've always assumed. These gaps are the key. They won't close until we stop treating interstellar objects like exotic versions of the familiar and begin to treat them for what they might really be: unfamiliar things that happen to be passing through. The possibility of artificiality, uncomfortable as it is, won't vanish. It will remain lurking at the edges of our conversation. Not because it's likely, but because we can't fully disprove it. And as long as our natural explanations continue to require elaborate, sometimes implausible scaffolding to hold up, it will remain a whisper that reminds us the universe isn't obligated to populate itself only with objects that fit our models. Part 14. Hollow objects, shell worlds, and structural degeneracy. Let's entertain a thought experiment for a moment. Imagine you have two objects with identical mass. One is a solid sphere of rock, dense and homogeneous all the way through exactly what you'd expect from gravitational collapse and thermal equilibrium. The other is a hollow shell, like a giant beach ball, but made of metal. Thin walls enclose empty space, whether naturally formed or engineered by a process we don't fully understand. From the outside, the two objects would appear identical. Both reflect light the same way. Depending on their surface composition, they both have the same total mass. If you orbited them, they would exert the same gravitational pull. But here's the critical difference: their internal structure is completely different. That difference has far-reaching implications for how these objects would respond to external forces. Now, ask yourself, if you were observing these objects from a distance, inferring their properties based solely on how they move and interact with forces, could you tell them apart? The answer is no, not without additional data beyond what optical astronomy can provide. Why? Because mass is a scalar quantity. It's just a number. A kilogram without any direction or internal complexity. It doesn't tell you how that mass is distributed within the object. A kilogram of rock and a kilogram of hollow metal have the same mass, but their internal configurations are fundamentally different. Gravity treats them the same when calculating orbits or trajectories. Known gravitational forces, outgassing, radiation pressure, depend primarily on surface area and reflectivity, not on the inner structure. This is called structural degeneracy, the idea that different internal configurations can yield the same external measurements. It's one of the inherent limitations of how we infer properties of distant objects. When we're relying only on photons and orbital mechanics without being able to sample the object's interior, it's like looking at the surface of a mystery without understanding what's beneath. You see the surface, measure the mass, and all the rest is educated guesswork based on assumptions. Now, let's consider what this means for 3I, Atlas. What if it's not homogeneous? What if it's not a solid mass of ice and rock, as we typically assume comets to be? What if its internal structure is layered, or even hollow, with mass concentrated in unexpected ways? If the mass is concentrated in a dense outer shell that surrounds a low-density core, or worse, a void, then the mass inferred from brightness and albedo would overestimate the total mass, as we would be assuming uniform density throughout the entire volume. But the mass inferred from the outgassing response might underestimate it, because we'd treat the object as lightweight, easy to accelerate. In reality, though, the outer shell might be much more responsive to forces, because it's thin enough to react dramatically to outgassing, while the dense interior barely notices. This could explain the paradox perfectly. The CLO team's observations saw no deviation, because the object's total mass is higher than the December estimate suggested, giving it the inertia to resist weak, diffuse force. Enceladus, with its mysterious subsurface ocean beneath an icy shell, presents a prime example of how even celestial bodies that appear relatively simple on the surface can hide complexities beyond our initial understanding. We only discovered its hidden layers after spacecraft ventured close enough to measure gravitational anomalies and observe geysers erupting from cracks in its icy crust. Europa, Ganymede, Titan, each one a moon with intricate, multifaceted internal structures that defy the assumption that their surface appearance is all there is to know. This raises an intriguing possibility for 3I Atlas. What if a comet, too, could possess an anisotropic structure? What if it's something smaller, a celestial body that never underwent the full planetary differentiation we see with larger objects, yet still developed a layered interior? What if, in ways we haven't yet grasped, such bodies can form with complex inner structures, engineered by nature or cosmic processes beyond our comprehension? Material science offers us relevant analogies. Consider composite structures, such as carbon fiber, honeycomb panels, or aerogels. These materials achieve exceptional strength while keeping mass low by strategically distributing material, rather than packing it uniformly throughout. The principle here is efficiency, placing material only where it's needed for structural integrity, leaving the rest as void or low-density areas. Nature does this, too, and has been doing so for hundreds of millions of years. Birds' bones are hollow, offering just enough strength to endure the impact of landing while keeping them light enough for flight. Plant stems are tubular, strong enough to support their structure, but light enough to reach toward the sky without collapsing under their own weight. Even microscopic algae, called diatoms, create intricate silica shells with voids that maximize surface area while minimizing material costs. Nature's economy is one of structural efficiency, where material is distributed optimally rather than uniformly. Could 3I Atlas be a comet constructed in a similar fashion? Perhaps it has a dense outer layer, enriched with rocky or metallic materials, but conceals a hollow or porous interior. This could explain the discrepancies in our observations. If so, the mass inferred from brightness and albedo measurements would overestimate the total mass, because we would be assuming the body has uniform density throughout its volume. The typical method involves calculating the size based on how much light reflects back from the surface. Assuming it's solid ice with a density of around 500 kilograms per cubic meter, multiply this by volume, and you'd arrive at a mass that's likely too high, because much of the interior could be empty or composed of much lower density material than we've accounted for. However, the mass inferred from outgassing behavior could underestimate the true mass. This is because, with a porous or hollow structure, outgassing could be far more effective in producing thrust than it would be in a solid object. The gas jets would exert their force on the shell, which could respond more dramatically to localized forces, making the object appear lightweight and easily accelerated when it is, in fact, much heavier than we've calculated. The Clos observation, which showed no deviation from the predicted path. They would make sense in this context. The object's total mass is likely higher than the December estimate, giving it enough inertia to resist weaker forces acting on the whole body. But when it neared perihelion, when outgassing intensified, the active regions of the object, likely located on a thin outer shell, responded more dramatically to those forces. This could explain the sudden acceleration that the Forbes and Butler observation recorded, as these regions, lighter and thinner than expected, generated more forceful responses to outgassing than a solid, uniform body would. Here's where the situation gets complicated. The truth is, we currently have no reliable way to test this hypothesis remotely. We can't probe an object's internal structure using optical telescopes. The light from the surface, even infrared, only tells us so much. To investigate further, we'd need radar systems capable of penetrating the surface, or seismic tools that could measure vibrations through the object's interior. What we truly need is a spacecraft flyby, one equipped with penetrating instruments like ground-penetrating radar or gravimeters sensitive enough to detect density variations. These tools would allow us to map the interior, shedding light on whether 3I Atlas contains hidden layers or voids. Unfortunately, we don't have access to any such methods for 3I Atlas. It came, it passed, and we could only observe it with optical telescopes that offer a limited view, just the surface. The hollow shell hypothesis, while plausible, fits the data surprisingly well, and it can't be confirmed or ruled out with our current observational capabilities. This makes it both scientifically frustrating and intellectually stimulating. It's an explanation that can tie all the loose ends together, but offers no concrete predictions for what to look for next in interstellar objects. Without the means to get close, the mystery remains unresolved. This is not fringe science. It's not pseudoscience or wild speculation dressed up as a hypothesis. Structural heterogeneity in celestial objects is real. Comets are porous, as we've seen through missions like Rosetta, which visited Shestdesiatsedmp, Churyumov-Gerasimenko. It has a density of around 500 kilograms per cubic meter more void than solid. Asteroids, too, often have fractured, rubble pile structures where gravity barely holds together loose fragments. The possibility that 3I Atlas might have an unusual internal structure is not a leap into fantasy, but a grounded consideration rooted in our growing understanding of cosmic bodies. We know this from the successful missions of past spacecraft, like Rosetta, which visited Shestdesiatsedmp Churyumov-Gerasimenko. The comet's density is around 500 kilograms per cubic meter, meaning it is more void than solid. It's an intriguing insight into how comets can possess structures that are less about uniformity and more about complex internal architecture. Asteroids, too, are often more like rubble piles, held together loosely by the feeble grip of gravity, with fractures dotting their surfaces. This idea that 3I Atlas could have an unconventional internal structure isn't some far-fetched leap into the unknown. It's a straightforward acknowledgement of something fundamental: we don't actually know what's inside this celestial body. Simply assuming homogeneity because it is convenient for our calculations doesn't make it true. This is where astronomy faces a critical limitation. We're excellent at measuring light. Our instruments, with precision that can track photons from galaxies billions of light-years away, give us remarkable insights. We can measure chemical compositions from emission lines, track the movement of objects with remarkable precision, and even detect accelerations that, while infinitesimally small in practical terms, matter immensely in the realm of fundamental physics. But when it comes to understanding the internal structure of an object, we're often left in the dark. We rely on assumptions imported from other bodies we've studied, from comets in our own solar system to asteroids that have been catalogued, and from planets whose behaviors we've modeled extensively. We assume these bodies are similar, that a comet from interstellar space will have a comparable composition, density, and internal structure. Most of the time, these assumptions hold true, but what happens when they don't? What if an object formed under radically different conditions? What if it came from a protostar system with different compositions, different solar dynamics, or experienced processes we've never observed collisions? Thermal evolution. Chemical reactions that don't happen in our solar system. This is where 3I Atlas stands apart. It could be an object whose structure doesn't align with our assumptions about homogeneity. The takeaway from this isn't that we need to abandon our models entirely, but rather that we must recognize their limits. It reminds us that mass, as we understand it, isn't as straightforward as we'd like to think, especially when we can't directly measure it. Inferences, after all, are only as strong as their weakest link. If that link is based on assuming uniform density when we don't have other clues, the entire chain of logic becomes fragile. When we're dealing with objects we can't physically touch or sample, sometimes the most honest answer to what is this made of is simply, we don't know. And there's a critical distinction here. It's not we don't know anything, but rather that we know some things with confidence, and others we're inferring from assumptions that may not hold. Recognizing this distinction is key. It's the difference between scientific humility and uncertainty, between acknowledging the limits of our knowledge and admitting defeat. And that brings us to the real story here. It's not the mass discrepancy, nor the outgassing paradox, nor even the whispers of artificiality or exotic structures that are drawing attention. The real lesson from 3I Atlas is what it's teaching us about the fragility of certainty. It demonstrates how quickly confidently held assumptions can unravel when the data refuses to cooperate. More than that, it reveals a deeper question about how science communicates itself to a world that often demands simple answers to complex phenomena. Part 15. What 3I Atlas is really teaching us. Let's take a step back and review what we know with certainty about 3I Atlas. It's an interstellar object, making its journey across the vast space between stars before gravity bent its path toward our solar system. It passed through our cosmic neighborhood in 2025, closest to the Sun in mid-year, and then continued its voyage. Already too faint for most telescopes to track, near perihelion, it exhibited outgassing, releasing gas and possibly dust as solar heating triggered volatile materials on or beneath its surface. We know that multiple teams, equipped with state-of-the-art instruments from ground-based telescopes to space observatories, observed it, and their findings were published in peer-reviewed journals. That's the bedrock of what we can say with genuine confidence. But here's what we don't know. What's its mass? Is it 33 trillion kg? 260 billion kg? Or somewhere in between? We don't know. Its size, 5 kilometers across, 1 kilometer. That depends on assumptions we can't directly verify. Its density, is it fluffy, like solar system comets? Or denser, more compact? made of materials we haven't encountered before. We can only guess. What about its internal structure? Is it solid, porous, layered, or hollow? We have hypotheses, but no means of testing them. We detected some molecules, inferred others, but its complete chemical inventory remains unknown. Its thermal properties. How does heat travel through it? We've built models, but those models aren't measurements. Its rotational state. Is it spinning, tumbling, stable, or chaotic? The data is ambiguous. And its outgassing geometry. Where are the jets? How are they oriented? Are they symmetric or wildly asymmetric? We've made educated guesses based on what we can see. But there are many parts we can't observe that would give us the answers we need. The December acceleration, was it an anomaly? Or was it the Clo observation that was the outlier? We simply don't know yet. The unknowns far outnumber the knowns, and that's not a failure of science. It's a recognition of the limitations of our methods. This isn't evidence of incompetence. It's just the reality of our observations. We observed a point of light moving across the sky, a dot too far away, too small, to resolve into anything more than a pixel. From that single point, we've tried to infer everything about it, its composition, its origins, how it behaves, why it behaves the way it does, all from fragments of indirect information, photons, trajectories, curves, spectra, and orbital residuals. That's all we have. The fact that we've narrowed down the possibilities to a few competing hypotheses is remarkable in itself. Think about it for a moment from light alone, from measuring its brightness, its color, how those colors change over time. We've deduced its chemical composition, from motion alone, from tracking its position against the stars. We've calculated mass, estimated size, detected forces too small to measure directly. The fact that we can narrow down the possibilities to a handful of hypotheses, each one testable in its own right, is a testament to the power of observational astronomy. But the fact that these hypotheses contradict each other serves as a reminder that inference is not measurement. Models are not truth. Certainty in science is always provisional. It's based on the best available evidence, updated as new data comes in, and always held with the understanding that tomorrow might bring data that shifts everything we thought we knew. 3. Atlas didn't just cross our solar system. It crossed the boundaries of what we can confidently claim to know about objects we cannot visit. In doing so, it's exposed the uncomfortable reality of scientific knowledge, the gap between what scientists understand and what is communicated to the public. When the first mass estimate of 33 trillion kg came out 5 kilometers diameter, it was presented with confidence, not because the researchers were certain beyond a shadow of a doubt, but because that was the best available estimate. That's how science communication works. You present the best estimate. Error bars attached. But often, those error bars get lost in translation. Headlines proclaimed it. Press releases cited it. Science journalists reported it as fact, and it became the truth about 3I Atlas. Not because it was proven beyond doubt, but because it was the best available information at the time. Scientists are trained to speak confidently about their best estimates. Confidence signals competence. But when the December paper came out, suddenly, the truth shifted 260 billion kg. Became a completely different object, the same point of light, but now possessing an entirely different set of physical properties. And the natural question is, how did we get it so wrong the first time? Was it the instruments, the analysis? Was there a simple error that turned into a 100-fold discrepancy? But perhaps that's the wrong question to ask. The true question, then, is not how accurate we should have been initially, but how certain we were allowed to be in the first place. If the uncertainties were always present, lurking beneath our assumptions, if the inference chain we built was fragile at its core, dependent on assumptions about mass, structure, and composition that we couldn't truly verify, if those error bars were always wide enough to accommodate drastically different interpretations, depending on which assumptions we chose to anchor our theories to, then the shift from one estimate to another is not a failure. It's simply an update science unfolding as it is supposed to. This is the natural progression: gather data, create models, make predictions, refine with more data, and revise our models again. That's how we inch closer to understanding. But that's not how it always feels to the public, or even to fellow scientists in adjacent fields who are not immersed in the intricate complexities of small-body astronomy. To them, it can feel like chaos, a labyrinth of confusion where experts can't seem to agree on even the most fundamental facts. It can make you wonder, are all those confident press releases just cleverly disguised guesswork in a way? That's true, we don't know. Not with the kind of certainty that comes from direct measurement, the kind you get by weighing something on a scale or analyzing it in a laboratory. What we have are models, sophisticated mathematical frameworks that link what we can observe with what we want to understand. We have data, thousands of measurements collected painstakingly over months. We have inferences, logical chains that connect visible phenomena to the invisible truths we seek. We have hypotheses, explanations that fit some of the evidence but not all of it. Each internally consistent but at odds with one another, we find ourselves holding a paradox, one that might resolve with better data, more observations, longer baselines, or more refined instruments. Or perhaps it will require rethinking the very assumptions that shape how we perceive mass, cometary behavior, or how objects from distant star systems behave compared to their solar system counterparts. This is the essence of science at the frontier, the messiness of it all. It's not about textbook knowledge, neatly categorized, where every question has been answered, and every concept explained down to the last decimal. No, this is science as an ongoing, live process of discovery. It's full of false starts, revisions, contradictions, and uncomfortable ambiguities. It's in the papers that propose a solution, only to have the next set of data completely dismantle it. It's in the researchers who may disagree strongly on interpretations, but agree on the raw data. It's in the uncertainty that can't be erased simply by working harder or smarter, because some uncertainty is inherent to the problem itself. And this is what 3i Atlas is teaching us: humility. Not the kind that insists we know nothing that would be both false and paralyzing. We know a lot. We know it comes from another star system. We know when it arrived and when it left. We know it exhibited outgassing. We know its general trajectory. But it's the kind of humility that says, yes, we know some things, but we are uncertain about many others. And that distinguishing between the two is far more challenging than we first realized. It's a humility that acknowledges the difference between what we have directly measured and what we have inferred through layers of assumptions. It's the humility that resists the urge to present provisional conclusions as final facts just because uncertainty makes people uncomfortable. This is teaching us that classification systems, comet, asteroid, interstellar object, are useful only up to a point. These categories are human constructs, cognitive tools that help us organize knowledge and make predictions. But nature doesn't care whether an object fits neatly into our taxonomy. Nature doesn't conform to the boxes we draw. It creates a continuum. We put boundaries around parts of it, assign them names. But when something doesn't fit neatly between those lines, when it blurs the boundaries or combines properties of multiple categories, that doesn't mean the boxes are wrong. It simply reveals that they were approximations all along. 3i Atlas is teaching us that interstellar space isn't just a bigger version of our solar system. It's not a scaled-up version of the Kuiper belt. Stretched out across galactic distances, objects from distant star systems, born in protostellar disks with vastly different compositions, around stars of different masses and luminosities, could behave in ways that defy our models. They might be composed of materials we haven't yet encountered. Their structures might challenge everything we think we know. They might respond to forces in ways that surprise us, not because the laws of physics are different, but because the conditions in which they were formed and evolved differ from anything we've seen in our solar system. These interstellar objects might not be made of the same stuff as the comets and asteroids we know so well. Their formation could have followed an entirely different path, shaped by forces and processes we've never witnessed. And until we visit them directly, until we can send spacecraft to intercept these visitors, to sample, analyze, and measure their properties up close rather than from millions of kilometers away. We'll keep encountering surprises. We'll keep finding that the solar system-derived intuitions we have don't always translate cleanly to these foreign bodies. Perhaps most importantly, it's teaching us that paradoxes are not signs of failure, they're opportunities. Each time a dataset refuses to fit our models, every time observations contradict each other in ways we didn't think were possible, each time a model breaks down and can't be adjusted with simple parameter tweaks, we learn something profound. We learn where the limits of our understanding lie. We learn which assumptions are robust and hold across a range of contexts, and which are fragile, contingent upon specific conditions that might not apply universally. We are being forced to ask better questions, not just what is 3I Atlas in some simplistic, reductionist sense, but what can we actually know about objects like this? Given our observational constraints, which of our methods are reliable, and which ones break down at the edges? And how do we communicate scientific uncertainty without eroding public trust in science itself? Will we figure out what 3I Atlas is, eventually, most likely? Better data will come. Orbital models will stabilize. And researchers will continue to analyze archived observations using improved techniques. Someone will likely propose a theory that accommodates all the observations without requiring a series of unlikely coincidences. And that explanation will slowly become the consensus. Research papers will cite it. Textbooks will mention it. And the paradox will be resolved, filed away as an old confusion, now cleared up with our expanded understanding, or maybe it won't. Maybe 50 years from now, astronomers will still be debating whether 3I Atlas was a comet with extraordinary thermal properties, a structurally unique object, or something else entirely that doesn't quite fit any category we have yet devised. It may become one of those ongoing mysteries that's revisited every few decades by a new generation of researchers who think they've found the missing piece only for that piece to fail to fit the puzzle as neatly as hoped. And that's okay. Not every mystery is solved neatly. Some linger unresolved, reminding us that the universe is under no obligation to make sense on our timeline. Some questions are harder than they seem, and the absence of a definitive answer doesn't mean the question wasn't worth asking in the first place. What matters is that we continue our search. We keep asking questions, even when the answers are unsatisfying or ambiguous. We resist the temptation to force unclear data into tidy narratives. Just because uncertainty makes us uncomfortable, just because admitting that we don't know feels like admitting defeat, we treat science as an ongoing conversation, a dialogue between what we know, what we think we know, and what we have yet to discover, because somewhere out there, right now, in the vast expanse between the stars, another interstellar object is traveling along a trajectory that will eventually bring it into our solar system. It might arrive next year, detected by automated surveys that pick up a fast-moving object with a hyperbolic orbit, or in a decade, giving us time to prepare better instruments and interception missions. It might not come for a century, well beyond our lifetimes, but still within the scope of human civilization, if we're fortunate. And when it does, it will bring its own paradoxes, its own challenges, its own opportunities to discover something we didn't even know we didn't know. 3I Atlas didn't just pass through our solar system, it passed through the limits of our certainty. It has shown us that the frontier of knowledge is not a fixed line we've drawn between what we know and what we don't. It's a horizon that recedes the closer we get to it, always out of reach, always pulling us forward into the vast unknown. Every answer we find leads to more questions. Every paradox we resolve opens the door to deeper mysteries. And that, above all, is what makes science worth doing. Every answer we uncover sparks a cascade of new questions, pushing us deeper into the unknown. Each paradox we unravel only leads to further mysteries, layers we hadn't imagined. But this isn't a cause for frustration. It's the very essence of what makes science so compelling. The endless pursuit, the joy of discovery, is built on this process of perpetual questioning. Each answer adds another puzzle piece to the grand, cosmic picture. And with every step forward, we find ourselves standing at the edge of yet another horizon. This relentless drive to understand, to push boundaries, and to uncover truths is what fuels the curiosity of the human spirit. Science is not just about finding answers, it's about embracing the journey of exploration, knowing that with every answer we find, the universe will always have more to teach us. And that is what makes it so profoundly worthwhile.